Okay, good morning. So let us start the last part of this module. As I said, for some reason the projectors are not working. If you can have the lecture notes in front of you, that would be, of course, better. But otherwise, we can somehow survive. Yeah, it's a little bit hard, but I mean, hard for me, not you. Okay. The first thing we want to talk today is about Rolle's theorem. Rolle's a mathematician, so we want to know what he's talking now. And the problem is the idea is simple. So if you have a function f, okay, which is continuous on the closed interval a and b, but is differentiable on the open interval a and b. So I have one condition here, another condition. The third condition, which is important, is that f calculated at the left end point is equal to f calculated at the right end point. So if I have a function with these three properties, then the conclusion is that. So these three dots means we can conclude that there exists, this symbol means there exists a C in the open interval a and b, such that if you calculate the derivative at that point, it becomes 0. Okay, so that's the Rolle's theorem. And it is, I mean, intuitively it is very easy to understand why that is the case. So, for example, if I have, let us say that here is point A, here is point B, and I have a function which is continuous on the closed interval a and b, and it is differentiable everywhere within the interior points of a and b, and then I know that wherever I start, I will end up at the same height, then it is guaranteed that there is a number so that the derivative is 0. I hope that you can immediately understand that. For example, what is the content? The content is that I start from some height, so let us say that this is f of a, but be careful, I am supposed to return back to the same height when I reach here, so this means that here fa and fb are both equal. I start from this point and I end up at the same height. I have to go in a continuous and differentiable way. So it means that somehow it means that in any way that I go and come back here, okay, there is at least one point within this interval whose derivative is 0. For example, in this case, you might see that, okay, here is one of those points that you can have, yes, because if I draw the tangent line here, the tangent line is horizontal. So if this is the graph of the function f, if I ask you what is f prime of c, you would say that this is the slope of the tangent line at the point with x coordinate c, and because this is horizontal, this is 0. So that is mainly the content of the Rolle's theorem. Okay, so of course it might be more than one. Yes, for example, might be even this one is the case. If the tangent line is horizontal, that is also possible. I can have more bumps. But in order to understand this a little bit better, do you think I can relax one of these conditions and still the theorem holds? So that is good to understand. So my question is that, do you think continuity is essential for this theorem to hold? Yes. Do you think differentiability is also vital for this theorem to hold? In other words, can I relax it and make the result stronger or not? Continuity, I think, should be clear for you, that I cannot relax it, yes? Because if I relax continuity, I might have the same situation. So, for example, I can start from here and go up to there, for example, and then I can fill this up. And then I come back here, for example, from here, and then I go there. So you see, I am respecting all conditions. Of course, if I remove this continuity, automatically differentiability is also gone. But you see that in this picture, if the function is not continuous on that interval, there is no guarantee that I can have such a number. Yes? But let us keep continuity and relax differentiability. Do you think the theorem still holds or not?
No, because then we can have a function that does not have a point.
Can you, for example, can you give me an idea how to draw that graph? So, for example, I want to keep this A and B, and I want to keep the heights the same. So wherever I start, I want to end up the same way. I want to keep continuity, and I want to relax differentiability, and I want to show you intuitively that there is no guarantee that I can find. Yes?
Just two lines with an acute angle.
Yes, for example, I can go from here to here, yes, and then come back here, yes? So you see this function is continuous. It starts and ends at the same height. So I am respecting these two conditions, but I am not respecting this condition. Why? Because at this point, it is a sharp point, so it is not differentiable. And you see immediately that there is no guarantee that there is no guarantee that such a C exists. Yes? So there is no C whose tangent is horizontal. I mean, there is no C between, so that the tangent line for the graph is horizontal. Is that understandable? Yes? And I hope that you agree with me. Can I relax this condition?
No.
No, because then, of course, I can start from here and go somewhere here, yes? This is A, this is B. This function is continuous, differentiable, but I am not respecting this condition. And then you see that immediately the result does not hold. Is that clear? So all these things is needed. And then if that is the case, it is guaranteed that you can find such a C. So at intuitive level is easy, but the proof is a little bit more technical, so we skip the proof. Okay, but now let us go and can you see example 1 now? Yes, please.
If there can be like contrapositive too, so if there is no C such that it's zero, that means one of those conditions has to be false.
Yes, in principle, yes.
Okay.
But then it will be or.
Yeah, one of them has to be false.
Yeah.
Okay.
Okay. So, for example, can you see example 1 now?
The polynomial one?
So, yes, example 1 show that the polynomial p of x equals to, let me write it down here. So, example 1, right here, there is no notes. So, example number 1, the polynomial is given to be p of x equals to x to the power of 5 plus 2x to the power 3 minus 5x minus 10. Okay, this is the polynomial given, and I want to show that this polynomial has exactly, so underline the word exactly one root in the interval from 1 and 2. Yes, this is what I want to show. Okay, so this theorem, this problem has two parts. First of all, we have to guarantee the existence of a root between 1 and 2, and then we have to guarantee that this is the only one, there is no more. So that's the meaning of the word exactly. The first part I think is easy. What do you think I will use for the first part to show the existence of at least one root? Intermediate value theorem. So do you remember, for example, I calculate p of 1, so I would say that p of x is a polynomial and continuous everywhere, including, for example, a closed interval 1 and 2. On the other hand, so what I have, when I calculate p of 1, let us see what happens. I put 1 here, so it becomes 1 plus 2 minus 5 minus 10, which is how much? 3
Minus 12.
minus 12. And then when I calculate P of 2, so this is 32, and then plus 32 again, minus 10, so it becomes 44.
It's not.
It's 32 plus 16.
Yeah.
What?
32 plus 16.
Ah, yes, 16. 16. So what will be the answer then? 48, 38, 28. Yes, that's good. It didn't affect it. So then you see that these are negative. One of them is negative, the other one is positive. So in other words, P of 1 multiplied by P of 2 is negative. So this means that by intermediate value theorem, it is guaranteed that there exists a C in the open interval 1 and 2 such that P of C is equal to 0. Yes? So this part is actually a repetition of what we learned before about intermediate value theorem. This proves the existence, but the uniqueness is different. So, I want to prove that there will be only one. Okay, so let us say that this is not the case. We want to show, so let me, if I want to write everything, it will be too much. Okay, we will not have time. So I want to show that this is the only one. If you believe in me, the fight is over. If you don't believe, it means that you will still believe there is another C within the interval 1 and 2 for which P of C is 0. Yes? So it means that we've proved that this C in 1 and 2 is unique. If not, for example, let me call it C1 in 1 and 2, such that, can you fill it up for me, such that what?
F of C1 is 0.
P of C1
P of C1
is 0. So do you agree with this? So if you don't believe that this is the only one, it means you believe there is another one. This another one means C1 and C2 are different, okay, when you say there is another one. But now you see P is continuous on 1 and 2, because polynomials are continuous everywhere. P is differentiable everywhere, of course, even on the open interval 1 and 2. One more thing, we know P of C is equal to P of C1 because both of them is 0. So this means that I have 3 conditions of the Rolle's theorem in place. So this means that according to Rolle's theorem, what can I conclude?
that there must be some.
There must be, let me call it C2, so let me call it alpha. Yes, there exists an alpha where between C1 and C2, so because I don't know which one is greater, so let me don't write from C to C1 or from C1 to C2. There exists alpha between C and C1. Yes, such that, okay, complete it for me, such that what happens?
P prime of
P prime of alpha is equal to 0. Yes? The reason I didn't write the interval C and C1, because I know C1 and C and C1 are different, but I don't know which one is greater. So I don't use the interval notation. Yes? I just say between C1. Everyone understands that? Yes or no? Mm-hmm. Okay, but let us see if I get a contradiction or not. If I want to calculate P prime of x, so in order to calculate P prime of alpha, first let me calculate P prime of x. So what is P prime of x? Very simple. So it is 5
x to the power of 4.
X to the power of 4 plus 6x to the power 2 minus 5. Is that right?
Yeah.
And then P prime of alpha is 0. This means that 5 alpha 4 plus 6 alpha squared minus 5 is 0. Yes, we have to admit that this is the case. But if you look closer, it is a contradiction. Why is that? Because let me tell you, where is C1 and C2? Where is C and C1? Both of them are between 1 and 2. So if you imagine This is the x-axis. So here I have 1, here I have 2. I know C1 and C2, C and C1, both of them are inside here. I don't know which one is greater than the other one, but for example, for definiteness of discussion, let us assume that C is here, C1 is here. But both of them are between 1 and 2. Okay? But where is alpha now?
In between them.
Alpha is between C and C1. So this means that alpha will be somewhere here. Okay? Do you agree? So if alpha is between C and 1, because C and C1 are between 1 and 2, it means alpha is greater than 1. Yes? So the conclusion from here is alpha is greater than 1. Is that understandable? Yes. But if alpha is greater than 1, this cannot work. Because if alpha is greater than 1, this is greater than 5, this is greater than 6, so this will be greater than 11. If a number greater than 11, I take 5 from it, it cannot be equal to 0. So yeah, because to save time, I want you see the video recorded later, but you have to write these things in the exam. Yeah. Is that understandable? So this is one way that you use Rolle's theorem to prove the uniqueness. I see some question marks on your heads. Understandable or not?
So there are 2 steps.
Yes, even they say exactly, you have to do it in 2 steps, because the intermediate value theorem only guarantees the existence. But there might be more than one. But when they say no, prove that there is exactly one, it means that first you prove there is one, and then show that there is no more than one. Usually there is no more than one. You need to remind yourself about the Rolle's theorem or some other method that we will see a little bit later. Is that understandable? Yes or no? Yeah. Happy? Okay. So now let us go to the second question. Again, so example 2, show that this equation x plus 1/2 over 1/2 sine x equals to 1 has exactly 1 root. Okay? Okay, so let us go to the board. So this one is example 2. So the equation is x plus 1/2 sine x equals to 1. Okay, again, I want to show that there exists only one solution, and they haven't told us in any kind of interval, so it is up to us to decide. I mean, sometimes it is a little bit tricky to find the correct one. But this is an equation. All the theorems we have, I mean, the intermediate value theorem needs a function. Rolle's theorem also needs a function. So for the time being, I do not have any functions at my disposal. I have just an equation. So if I want to apply one of these or both of these theorems, what do I need? I need a function. So do you have experience what your function should be?
That set to 0.
Minus 1 equals to 0. So I mean, so this equation is equivalent to saying that x plus 1/2 sine x minus 1 equals to 0. Okay, so then I would say let f of x be equals to x plus 1 over 2 sine x minus 1. Okay. So first, you want to use intermediate value theorem, so you need continuity. This should be phrased in the exam. Is this function continuous? How do you defend that? This x is a polynomial, it's continuous. Sine x is everywhere continuous. So if I multiply a continuous function by a number, it will remain continuous. And if I add or subtract continuous functions, it remains continuous. So you should explain a little bit why this function is continuous. Okay, so it is continuous. Everywhere, yes? What about differentiability? It's also differentiable because we saw that all of them are differentiable everywhere. So it's also differentiable everywhere. So we don't have any problems with these. Everywhere, yes. Okay, but now I want to ask you, what do you think? I want to prove the existence of a zero for this function. So in principle, you should use intermediate value theorem, but the point is that no interval is being proposed to us. So you have to be a little bit creative. I don't know which one you choose.
Minus 10.
I would prefer 0 first.
Yeah.
Yes, because it gives me -1.
Yeah.
So if I calculate f of 0, what happens? This becomes 0 plus 1 over 2 sine 0 minus 1, which is -1. I have my negative number, but I now need one positive number. So then, of course, you can be a little bit creative. So for example, let me calculate f of
1.
let me make it more clear. So let me calculate f of pi. Yes? F of pi. F of pi is pi plus 1 over 2 sine pi. Yes? And then minus 1. So sine of pi is 0, so it becomes pi minus 1. So this one is negative. Pi is 3 point something. It's positive. So anyway, so you see the interval is not proposed, so you have to find your own way. So, but that is correct. So it means that one of them, so at least what I can say that there exists by intermediate value theorem. Can you tell me what should I write? There exists what? A C where, in my case, between 0 and pi, such that when I apply f on C, the answer becomes 0. Yes? So this proves the existence of the solution. Yes? But now, so this is the existence part, yes? Existence part. Now I want to prove the uniqueness part. So, now you have experience, again, using the proof by contradiction. Let us say that this is not the case. If not, what does it mean? It means there is, let me write with the same notation so you are not confused. There is another C1 in 0 and pi such that okay, so but this guarantees that there is no root inside 0 and pi.
Can't we pick the interval?
Okay, so let me not choose an interval because that's not a good idea. Okay, so let me write. So if not, it means that there is another, where is it? I don't know. There is another C1 such that f of C1 is also 0. Okay? Okay, but the good news is that the function is continuous everywhere and differentiable everywhere, so you can limit it to any interval that you like. So even if this C1 is not within that interval, it is somewhere, then you can make an interval containing both of them and use that interval. Is that understandable? So here I don't know where C1 is indeed, because there was not interval given in the beginning to the problem. I used 0 and pi to be able to do my work. And now it is guaranteed that there is a root between 0 and pi. I am saying that there is no other root anywhere else. If you don't agree with me, then it means you have to agree that there is a C1 where I don't know, so that f of C1 is still 0. So wherever that is, so for example here, you have 0 to pi, so you know that C is somewhere here. C1 exists somewhere. Is it inside or is it outside? It doesn't matter. For example, let us consider it is outside. Then I can consider this bigger interval and write the Rolle's theorem for this bigger interval. So it doesn't matter. Yes, is that understandable? Okay, because it is everywhere continuous and everywhere differentiable. I don't face problems with those. But then, if that happens, there is guaranteed that I can have another alpha. So therefore, okay, so let me write it. F of C is equal to f of C1 is equal to 0. Continuity is done. Differentiability is also done. So I can use Rolle's theorem. So Rolle's theorem guarantees what? That guarantees an existence of alpha between between what? C and C1, such that f prime of alpha is 0. Okay, let me wait for some seconds. Is that okay with everyone? Are you following or not? Yes, everyone? Okay? Nod your head at least. Yes, is that okay? Yes. If not, please ask me. Don't hesitate. Okay?
What is the function of C1 at this point?
What do you mean by the function of C1? F is the function I introduced from the beginning of my problem, and I'm working with the
function in general. Like, why do you choose C1?
The purpose. That's the
No. I'm saying I'm just following the same logic. You see, first I showed that there is a number C between 0 and pi, so that f of C is 0.
Yeah.
And I want to show that there is no more anywhere else.
Yeah.
If you don't believe in me, then you have to believe there is another one somewhere.
Yeah.
And then I am saying that if there is another one somewhere, it means that f of C1 should also be 0. And then this function is continuous everywhere, differentiable everywhere. And f of C1, according to what you told me, is 0. F of C is also 0, so it means f of C and f of C1 are the same.
Yeah.
So this means that I am meeting all these three conditions of the Rolle's theorem. So it means I am allowed to apply it.
Oh, so what does the theorem tell you?
The theorem tells you that there exists a C between those two numbers whose derivative is 0.
Oh, okay.
That's what I'm using. There is an alpha between C and C1 whose derivative at that alpha is 0.
Okay.
But I want to show you that this is a contradiction. This cannot happen. Why is that? In order to see why this is a contradiction, what you do first, if you want to calculate f prime of alpha, you have to calculate f prime of x first.
Yeah.
So I would say, but f prime of x is what? Let us do it. 1 plus 1/2 cosine. Do you agree this is the derivative? But f prime of alpha is 0. So this means that 1 plus 1/2 cosine alpha is 0. Yes? But this cannot happen. This is a contradiction. Why? Because this means what? I move 1 to the other side and multiply by 2. Yes? I moved 1 to the other side, minus 1, and multiplied by 2. So if you believe in what you said, you have to live with this consequence. But this is a contradiction. Why? Because cosine alpha is minimally minus 1, and it cannot be equal to 1. So I put this symbol for contradiction. So this contradiction is the result of your fighting with me. Yes, you fought with me that there is another one, but if there is another one, you have to live with this consequence, which is not possible. So that's the logic. So the uniqueness part is like this. Is that understandable?
There's no need to prove the continuity and differentiability.
Yes, it is.
Again,
But I have written it somewhere here. So in the exam, you have to write it in a clear way. But I want to because if I want to really write down everything, then there will be 1 or 2 problems we can solve. Yes? And the video is there, so if you forget, you can review that. Yes, please.
The sign for contradiction, I'm assuming that's also a valid sign for the exam. I'm guessing because
That's my invention somehow. So whenever I use this, I mean in contradiction. I don't think it is universal. I have seen it some professors use, but I don't think it's a universal symbol indicating contradiction.
Okay, so I should not risk it with the symbol on
No, don't do it in exam. Write it word. So don't be lazy. Yes? If you want to be lazy, I really always advise you against being lazy. But at least don't be lazy in the exam, okay? Yeah.
So, is there an example of like this solution written out in the full exam proper form somewhere?
I try to look into some of exams and I put them here, but in the lecture notes.
Okay,
If it is not there, it means I couldn't find.
okay, so
But there are some questions in the workshop problems that I addressed to solve.
Okay, and the solution papers will show the proper formatting of the.
Yes. Yes, and unfortunately I couldn't find the solutions in English. You can send an email to the examiner. I think there should be English version for the solutions as well, but these days translating them using ChatGPT is a matter of seconds, okay? It's a little bit trouble, but yeah.
The Swedish canvas.
Okay, so let me keep example number 3, but I just want to mention that example number 3 is a hard question. You have to be more creative. You see, I want to use Rolle's theorem not to prove the existence. Let A, B, and C and D be real numbers such that I have this property. Show that this equation has at least one root strictly between 0 and 1. Because usually this reminds you of intermediate value theorem, because it wants to show that there exists at least one. Okay? So far I have used Rolle's theorem to prove the uniqueness part. But I try to find an example that sometimes Rolle's theorem is also good to prove the existence part. I want to leave it for the time being so that we manage to cover everything. But I hope that you immediately see that intermediate value theorem is not suitable for this problem. Yes? If you want to show that this, can you see that? A plus, so I want to show, let me show it here. If I want to show that this equation, a plus bx plus cx squared plus dx cubed equals to 0, has at least one solution between 0 and 1, yes, this is it is the right format usually for the intermediate value theorem. So what do? You introduce a function, and then you say that this function is polynomial, is continuous, and then you usually calculate p of 0, which you get a, and you calculate p of 1, which you get a plus b plus c plus d. For intermediate value theorem to work, you need to confirm that these two numbers have different signs, which in this case is not that obvious. So this is why I think this is very similar to one exam problem. So that's why it came to my mind to write it here for you. If you have time, we can come back to it. Otherwise, I make definitely a video for it and then upload it later for you. But please think about it yourself as well. Okay, any questions? So now there is the second part, which is a very important theorem. That is the mean value theorem. So let us read the content so you can see that. Okay, let me write it here for you on the board because okay, so let me write mean value theorem, sorry, the mean value theorem. Okay, the first two conditions is exactly identical to the Rolle's theorem. So I have a function f. About this function I know two things. I know it's continuous on the closed interval a and b, is differentiable on a and b. Okay? In Rolle's theorem, I had a third condition. What was it?
F of a equals
F of a. But here we don't have it. We jump to the conclusion. But the conclusion is this. There exists a C where, in the open interval, such that when you calculate f of this endpoint minus f of that endpoint divided by the endpoint b minus endpoint a, it becomes the derivative of C. The derivative of f at C. This is the content of mean value theorem.
And the Rolle's theorem is just an extension of that, no?
Yes, this is correct. But if you see, this theorem is proved using Rolle's theorem,
Really?
not the other way around. Yeah, you are but completely right. What he's saying is that people think that, okay, it was better to prove this theorem because the Rolle's theorem then will be one specific particular case of this. Why? Because if I add that FB and FA the same, then the left-hand side becomes 0 and then I will get what I got in the Rolle's theorem. But the proof of this theorem goes through Rolle's theorem. So, yes,
What did that sign mean?
there exists. So I am using them a lot for all. This there exists. and this symbol means belongs to. Okay, so these are the symbols I use a lot. Okay, the proof of this is a workshop problem, so might be you can talk about it during your exercise lessons. But is it intuitively understandable for you? Can you tell me geometrically, intuitively, what the theorem means?
There has to be a point where the derivative is the same as the line.
Yeah, why is that? Because, for example, let me have this point A and this point B. I start from somewhere and then go to B, but I don't have to return back, but I have to go in a continuous and differentiable manner. Okay, for example, let me make it very simple to see what happens. So, for example, like this. Make it a little bit. Yes, this is a better one. So, for example, this function on the closed interval a and b is continuous, and within it, it is also differentiable. Okay, if I ask you, can you tell me the coordinates? Let me call this point A, let me call this point B. Can you tell me the coordinates of point A? The x coordinate is clear, and this function, I call it function f. This is A, and what is the f of A? This is the y coordinate. And the same story for B, yes? B and f of B. Do you agree? Okay, but now let me connect this point to this point. Yes? And I ask you, can you tell me what is the k value of this blue line? K value of AB.
That would be my
The difference, the delta y over delta x, the difference between y coordinates, divided by difference between x coordinates. So is that right? So this that appears here is actually KAB. This is the k value of this blue line. But now the theorem claims that if you do it in a continuous differentiable way, at least you can find one single point here so that the derivative at this point is equal to this. And I hope that you agree with me. Somewhere here, if I draw a tangent line, this tangent line will be parallel to this blue line. If this point is C, if I ask you what is the k value here, you should be able to answer that immediately. The k value of the tangent line at the point whose x coordinates is C is equal to what? F prime of C. Okay, so this means that if you do it in a continuous differentiable way, at least you will find a point on the curve so that when you draw the tangent line there, the tangent line becomes parallel to this line that connects the endpoints. So that's the content of the mean value theorem. Yes, please.
So why do you write continuous with square bracket and differentiable with normal bracket?
You cannot differentiate exact next point to it.
Because you know that, so that is, I can put also a square brackets around that. But the point is that when I say a square root, then because when I consider A itself in differentiability, you know that the derivative is the limit of f of A plus h minus f of A divided by h goes to 0, yes? So when you talk about derivative, h goes to 0, it means that h can be positive or negative, but very close to 0. If it is positive, then this number is a little bit more than A. But if it goes to the 0 from the negative side, then A plus h will be a little bit less than A. So by writing A and B, not including A, I am saying that what happens before this point doesn't matter for me. Yes?
So why do you write square bracket for continuous?
No, so you see, in mathematics, you want to make the theorems as general as possible. Yes? So that is not a big problem. The problem is that why I am taking this off. Because if I don't take this off and write square brackets there, it means for me, the derivative at A somehow needs some information about what is happening before this point A, which is not relevant to what I want in this
I
context.
understand, but for you should write square bracket instead of normal bracket.
Yeah, because you can go to infinity then. On A&B, for example. Like 1 over x.
No, because one thing is that because continuity because there were some things that I skipped, I had it in my notes. When I say a function is continuous on a closed interval, it means it is right continuous on A. That is part of the definition.
What if that point is missing? Does that theorem still apply? Applies, right? If the A
So
point
that's
is
a good
that-
question. Let me think about it. If that point is missing,
Then we don't have f of A now.
Yeah, no.
then there might be no guarantee. So it means that if I don't know that the function is continuous exactly at that point, then what happens?
If we make it like a straight line and f of A just pops out here instead, then there is no derivative of 0 between.
Yes. So it means that if I relax that condition, I am in trouble. Yeah, so what he's saying, I think, is correct. So what he's saying is that if I, for example, relax this one, then I might have this function like this. Yes? Yes, and then there is no guarantee, there is no endpoint there.
There is no f of A.
Yes, there is no f of A. So that's the whole point. Is that understandable?
Yeah.
So if you take one of them, it means that you are allowing this situation to happen, but then you see that there is no guarantee that I can write something like this.
Okay.
Yes, but I will think about it if I can come up with a better explanation. There should be a reason for that. For this one I know, because, what, pardon?
It's fine, I will just use it.
No, but you are right, that's a valid question. We have to have a definite answer for that.
Okay.
Yes. Okay, but now let us go and try to solve some problems. So one example we solve and then we have the break. Okay, so example number 4, I want to solve it together. So a number c is called a constant point of a function if f of c is equal to c. That is a definition. So I have informed you about what does it mean to have a constant point for a function. Show that this function f of x equals to sine of 1 over 2x has at most one constant point. Okay, so is the question clear? So the first part of the question is defining something for you. It tells you that when you have a function and you have a real number, this real number is called a constant of f if this works. Yes? For example, if I have this function f of x equals to x cubed, can you give me a constant for this function?
1.
1. Because f of 1 is equal to 1. Or another constant, f of 0 is equal to 0. So I have two constants for this function. But the problem claims that the function in the problem, a minus 1 is not. A minus 1 is also there. So there are 3 constants for this function. Okay? But so in principle, if I want to know the constant functions, how should I, the constant numbers, all of them, I would write f of c is equal to c. F of c is c cubed equal to c, and try to solve this equation. And if you solve this equation, you get exactly 3. 0, 1, and minus 1. So this is guaranteed that this function has 3 different constants, not more. The problem claims that the function introduced in the problem has only one constant point. Okay? First of all, I want you to understand that this is not as simple as this case. Let us say that you don't know the mean value theorem and you want to solve it yourself. How should you solve the problem? If you don't have access to the mean value theorem, so in principle you should say that I need to look for some c so that this is equal to that, but then you replace x with c and then put it equal to c. But this is a transcendental equation. It's not a trigonometric. It is a trigonometric equation because you see the angle that you are here looking for is also outside. Whenever you have these type of equations, you are in trouble. That is called a transcendental equation. Okay, so that's what I'm saying, that this answering to the same question for this function was very simple, but answering the same question for this one is a little bit harder. So I need a little bit more tools in my hand to be able to do. Okay, is that clear what I'm going to do? I want to show that there is no more than one constant. Again, we use if not. So let us say, assume that this is not the case. And C1 not equal to C1 and C2 are two. And by the way, for definiteness of discussion, let me say, because one of them should be less than one, or two distinct constants for f. I claim there is no more than one, but by the way, we don't know even there is one. In this problem, we don't care. We want to show there is no more than one. If there is one or no, we don't know. But of course, there is one. What is that? 0. If I put 0, sign of 0 is 0. So there is one, but there is no more than one. Okay? So assume that this is not the case, and C1 less than C2 are two distinct constants for f. So what does it mean? It means that f of C1 is equal to C1 and f of C2 is equal to C2. Yes, that's the meaning of being constants. But now, can I apply mean value theorem for this function on the interval C1 and C2? Yes, f is continuous everywhere, including C1 and C2. F is differentiable everywhere, including C1 and C2. Okay? So what can I conclude? Mean value theorem guarantees that there exists a C where between C1 and C2 such that what happens? Help me.
C2 minus C1.
F of the endpoint minus f of the this point, and C2 minus C1 is equal to f prime of
Some alpha.
f prime of C.
Yeah.
Is that right? I am using mean value theorem. But then what does it mean? F of C2, by my assumption is C2, so this becomes C2 minus f of C1 is C1 divided by C2 minus C1. But to calculate f prime of C, I have to calculate f prime of x first, which is what? Can you tell me? It's the chain rule. So do you remember? You have to take this u, pretend that u is x. The derivative of sine of x is cosine of x, so I pretend that u is x, so I can write it, but it is not finished yet. I have to multiply by u prime. This is the yesterday's lesson. But this then becomes what? Yes? Okay, but now I want f prime of c. It means that I calculate f prime of x, which I did, then I replace.
The fraction should be C2 minus C1 over C2 minus C1, right?
Yes, this is C2, thank you. Thank you. F of C2 is C2, F of C1 is C. Okay, and I know C1 and C2 are not equal, so I don't have any trouble in the denominator. So this means this is number 1, because C2 minus C1. And then 1 is equal to this, so it means that 2 is equal to cosine of 1 over 2C, and that is again my contradiction. Yeah, so that's also, so I want you to see that this mean value theorem is needed for solving this problem. It is not as simple as the previous case. Yes, you might find another way, I don't know, but that's at least one way. Any questions? Understandable or not? Yes? Oh. So we can have a break for 5 minutes and then we come back. Thank you.